Hello everyone, my name is Kushal and I'm a first semester ISAT student at Southeastern Louisiana University. The topic of my presentation is Fourier transform for audio manipulation. I have been quite fascinated with the idea of autotune. This is basically what singers use to decrease or increase their pitch just a little bit to sound a little bit different. Maybe an artist wants his voice to be a little bit deeper, or maybe he wants to decrease the pitch. I wanted to see if this could be done with Fourier transform, and this is what I explored with this project. Professionally, I'm an experienced software developer and technical project manager with experience working for various multinational companies. I've also done a lot of freelance work and also launched a few products. I've also done some open source contributions as well. I had a straightforward approach plan for this project since sound is on amplitude versus time domain. On FFT, it would convert into magnitude versus frequency. So by changing the frequency, I could actually alter the pitch of the sound. So at first, I specified a pitch factor higher than 1 to stretch and low to compress. Then I read the audio file. Then we apply fast Fourier transform to convert to frequency domain. Then I shift frequencies, either stretch or compress, depending on our pitch factor. Then we apply inverse Fourier transform to convert back to time domain, and finally save the modified audio file.
I fear darkness hunts us. Use what you've learned and stay the course.
0.8. This is the original
I fear
audio.
darkness hunts us. Use what you've learned and stay the course.
This is after a pitch factor of 0.8 is applied. Basically, this is supposed to make the pitch lower.
I fear darkness hunts us. Use what you've learned and stay the course.
I fear darkness
Let's try it again
hunts
with the pitch
us.
factor 1.2.
Use what you've
This is
learned
supposed to
and
increase
stay
the
the
pitch.
course.
I fear darkness hunts us. Use what you've learned and stay.
The approach worked, but there was an issue. I'm not sure if you noticed it, but to make it more clear, I decreased the pitch factor to 0.6, and on doing so, you can see that there's a lot of empty space over here. Basically, what's happening is I'm decreasing the frequency, but this is also somehow compressing the time of the recording. On the opposite scenario, when I'm using a pitch factor 1.6, you can see that the audio is actually not complete. This would align to somewhere over here, so we're missing a chunk of the audio. So this was an issue I noticed during the creation of the program, and I will talk about why it's happening in the next slide. So the software did work up to an extent, but we now have a problem. What's happening is the length of audio is staying constant. So for example, if the audio is 5 seconds, the output would also be 5 seconds. And if I'm trying to stretch the audio, it's also stretching the time. The frequency is changing, so is the time. So the output would always be 5 seconds. But since the time stretched as well, 5 seconds would not be enough to cover the whole recording. The same thing happens when I'm using a smaller pitch factor. If I use a pitch factor of 0.6, instead of 5 seconds, the audio finishes at 3 seconds, and 2 seconds were just empty noise. So I had to use a modified approach to factor for this, which I'll talk about in the next slide. The modified approach was actually quite complicated. This time I decided to do frame-based processing. Basically, we're using an algorithm to break the audio signal into overlapping frames to enable precise frequency manipulation. We use Fourier transform on each individual frame. Then we use advanced interpolation for magnitude preservation and phase correction. Then we reverse FFT. Then we also use windowing to reduce the artifact. And finally, save it to disk. As you can see in the results, when I'm using a pitch factor of 0.6, our previous problem doesn't exist. The sound actually is in the correct timing, and I was actually able to decrease the pitch. Similar results with higher pitch factor. The time perfectly aligns, and I can actually deepen a user's voice. So this did the job, and it did work pretty well. I will demonstrate how it works. I will demonstrate an example in the next slide.
I fear
This is
darkness
the output
hunts
audio
us.
after passing
Use
it
what
through
you've
the modified
learned
program
and stay the
with a pitch
course.
factor of 1.1.
I fear darkness hunts us. Use what you've learned and stay the course.
As you can see, our modified approach did work, and we solved our previous problems. However, as a software developer, I am trained to think of the most efficient solution to a particular problem. In this particular case, our approach just doesn't feel efficient. In terms of time and space complexity, the solution is exponentially more complicated than other straightforward audio manipulation algorithms. Uh, on research, I found out there were like really straightforward algorithms that could achieve what we achieved, and those were much more efficient than what we're trying to do. This approach also feels really over engineered. I mean, as a software developer, I would never use FFT for audio manipulation, and I came to the conclusion that audio manipulation might not be the right use case for Fourier transform. However, since I had already committed to the project, I just wanted to make sure that I can make it happen, and then I wanted to explore some more practical use cases, which we'll discuss in the next slide. While reading about FFT, I had read about how computers use FFT to save files and to save disk space. The idea was pretty straightforward. We just compute magnitude of all the frequencies in an image. We then specify a minimum threshold and discard all the frequencies that fall below the specified threshold. Then finally, we reconstruct the image using reverse FFT. So after using Fourier transform on an image, the results were quite staggering. As you can see, we are using top 90% of frequencies as our threshold, and with that you can see the image doesn't really look any different. I did use a bigger monitor to see if it would make any difference, but for a naked eye it looks exactly the same. But the interesting part is we are getting a 43.21% size reduction, so that's quite overwhelming. The observations were actually quite mind-blowing. 43% reduction in size without no visible difference is actually quite cool, and I feel like this is something I would actually use in my future projects. I did try some aggressive compression, and it did bring the size even further down even further, but you can actually tell the difference. So if I wanted to just decrease the size without decreasing the quality, then I would just use the method that I did earlier. And if I just maybe, let's say I wanted to create a thumbnail, then I would do more aggressive thresholding to decrease the size even further. In conclusion, I really enjoyed this class and I really enjoyed learning about FFT. I know FFT has a lot of use cases, and maybe I made a mistake by limiting it to audio transformation, but my initial idea led me to a tangent, and that tangent led me to image compression. This is something I'm going to be using in the future for image compression. No doubt I'm just going to be using FFT, but I plan to use it for video compression as well. For my ISAT project, I'm working on video processing, and the smaller the video size, the better it's going to be. So I intend to use FFT to compress the video size and to help me with other projects. Overall, this was quite a good experience. I feel really grateful for the opportunity to learn about FFT, and I want to thank the faculty and staff at Southeastern Louisiana University for the opportunity, and special thanks to Dr. Yoshida for introducing me to the topic. Thank you so much for your time. In the presentation, I talked about three approaches. The first one was a simple Fourier transform where the time was compressing as well as the frequency. The second one is where I solved the issue of time compressing and I was just able to alter the frequency. And the third one is image compression. All three of them are linked here. The simple Fourier audio transform is for our first approach, the complex Fourier audio is for our second approach, and the Fourier image compression is for the third approach. I feel like out of all three of them, the Fourier image compression might be an interesting topic for the faculty, staff, or maybe students at Southeastern to view. The link should be if you click on the link, you should have access to the file. You can just download it and run it on your own computer. Hopefully this is interesting, and I'm really thankful for your time, so thank you so much.